20 to 1, but jump to the 2025 and 2026 sources, and that golden rule has been completely abandoned, hasn't it?
It has. The chinchilla law is still mathematically sound if your only goal is training efficiency.
Hmm.
But the industry realized they were solving for the wrong variable. They deliberately abandoned compute optimality in favor of inference economics.
Ah, here is where the business reality violently collides with the mathematics. Explain the economics of inference for us.
Training a massive model happens once. It might cost $50 million, but it is a one-time capital expenditure. But serving that model-running inference for millions of users typing queries every single day is an endless, permanent operating expense.
And larger models require way more GPUs just to run.
Exactly. A 100 billion parameter model is incredibly expensive to serve. A 10 billion parameter model is vastly cheaper. So the labs realized it makes profound economic sense to spend massive, frankly irrational amounts of compute over training a much smaller model.
You waste money up front.
You waste money during a one-time training phase to permanently save money during the infinite inference phase.
So they completely ignore the 20 tokens per parameter rule.
They obliterate it.
Mhm.
The Llama 3.8b model used roughly 1,875 tokens per parameter, and the Qwen 320.6b model, which is a tiny model, reportedly hit an astonishing ratio of 60,000 to 1.
60,000 to 1.
They force-fed a tiny model 36 trillion tokens.
That's insane. It's like taking a compact car engine and forcing a swimming pool of jet fuel through it until the engine somehow becomes capable of warp speed. But force-feeding models this much data brings up the most terrifying projection in our entire stack of sources. The data wall.
Yes, the data wall.
Yeah.
Epoch AI published a rigorous projection analyzing the total effective stock of public, human-generated text on the internet. We are talking about every book, every article, every Reddit post, every public code repository.
Everything.
They estimate the total usable stock is roughly 300 trillion tokens.
And the projection of when we run out.
Based on the accelerated overtraining we just discussed, they project that this entire stock of human knowledge will be fully utilized between 2026 and 2032. The median consensus estimate is 2028.
2028, I need you, the listener, to really process that. 2028 is essentially tomorrow. We are going to exhaust the written history of humanity in a matter of months.
And this trajectory is actively being accelerated by the MIT Data Provenance Initiative findings. The web is closing its doors. Websites are rapidly updating their terms of service and their robots.txt files to aggressively block AI scrapers.
Right. The sources noted that a full 45% of the C4 dataset, which was one of the foundational open web crawls, is now legally restricted.
That's shrinking fast.
It is the ultimate technological irony. We built a machine whose singular source of fuel is human knowledge, and it consumed it so aggressively that we are literally running out of the internet.
Which is forcing an existential pivot in the industry. If pre-training is slamming into a physical data wall, you cannot get your intelligence gains from simply scraping more data. You have to get the gains from how you teach the model post-training.
Which perfectly sets up the next phase of our journey. The base model has eaten the internet. It is a giant, chaotic, autocomplete machine. If I take a raw base model and ask it, what is the capital of France? It might not answer me. It might just output, what is the capital of Germany? What is the capital of Italy?
Because it is just predicting what text looks like. It assumes you're writing a trivia quiz, so it generates more trivia questions. It possesses the geographic knowledge of Paris, but it has no conceptual understanding of what it means to be a helpful assistant answering a user's prompt.
So we have to teach it manners. We have to teach it behavior. This is supervised fine-tuning, or SFT, also known as instruction tuning.
SFT relies on imitation learning. Instead of feeding it raw internet text, we take the base model and show it highly curated pairs of data prompt and the ideal response.
Like, user, what is the capital of France? Assistant, the capital of France is Paris.
Exactly. We run thousands of these perfectly formatted pairs through gradient descent. We are teaching it the structural format. When a user asks a question, your role is to provide a direct, helpful answer.
But the sources are very explicit here about the ratio of data. While pre-training required trillions of tokens, SFT requires remarkably little, right?
Quality completely supersedes quantity here. The prevailing theory, heavily supported by the 2025 literature, is the superficial alignment hypothesis.
The superficial alignment hypothesis.
It posits that a model already learned all the facts, logic, and reasoning it will ever know during pre-training. SFT doesn't inject new knowledge. It merely surfaces the capabilities that are already latent inside the model. A few thousand incredibly high-quality human-written examples are entirely sufficient to unlock that latent potential.
However, SFT carries a severe risk, which the technical reports warn developers about constantly: catastrophic forgetting.
The neural network's capacity is finite. If you take a massive, generally capable model and you aggressively fine-tune it exclusively on Python coding examples for 10,000 steps, something dangerous happens to the internal weights.
What
It
happens?
becomes an exceptional Python coder, but it will literally forget how to write a sonnet or how to summarize a historical document.
This is also referred to as narrow tuning.
Yes, you pull the model's weight so hard in one specific vector direction that you irreversibly warp and degrade the rest of its generalized knowledge space. The mountain valley shifts, and it forgets the paths to other skills.
Okay, so SFT gives it the format. It learns to answer questions. But SFT doesn't guarantee the model won't output something highly toxic, politically biased, or just stubbornly unhelpful. You need a way to steer the tone. That is where alignment comes in, traditionally via RLHF reinforcement learning from human feedback.
RLHF is how you align the raw intelligence with nuanced, subjective human preferences. It is a complex pipeline. First, you take a prompt and you have the model generate multiple different responses. Then, human raters read those responses and rank them from best to worst based on helpfulness and safety.
And we use that human ranking data to train a second, completely separate AI model, right?
Correct. We train a reward model. The reward model learns to mimic the human raters. Once the reward model is trained, we bring the main LLM back in. We use a reinforcement learning algorithm, almost always PPO, proximal policy optimization.
Let's break down PPO conceptually. How does the reinforcement loop actually work?
The LLM generates a response. The reward model grades it, outputting a numerical score. If the score is high, PPO reaches into the LLM and adjusts its weights to increase the probability of generating that kind of text again.
Okay.
If the score is low, it penalizes it. The proximal part of PPO ensures the model doesn't take too large of a mathematical step at once, preventing it from completely breaking its own grammar just to chase a high score.
But the sources describe RLHF and PPO as notoriously brittle. They are incredibly unstable to train, and they take up a phenomenal amount of GPU memory because you have to keep the main model, the reward model, and the reference models all loaded into RAM simultaneously.
Which is exactly why the 2025 and 2026 industry standard rapidly shifted to DPO, direct preference optimization. DPO is a massive mathematical breakthrough in efficiency.
I loved reading about this because it feels like a cheat code. How does it bypass the memory bloat?
It mathematically reformulates the entire alignment process. The creators of DPO prove that you do not need a separate reward model at all.
Wait, really? No reward model?
None. Instead of using a complex reinforcement learning loop, DPO uses a single elegant classification-style loss function. You feed it preference pairs, a chosen response, and a rejected response. The algorithm directly updates model's policy to increase the likelihood of the chosen response and decrease the likelihood of the rejected response.
So it just collapses a massive multi-model pipeline into a simple binary contrast.
Exactly. It is vastly cheaper, highly stable, and mathematically equivalent to the optimal outcome of RLHF.
I also saw constitutional AI mentioned heavily in the Anthropic documentation.
Also known as RLAIF, reinforcement learning from AI feedback. Relying on human raters is slow, expensive, and humans often disagree with each other.
Yeah, humans are messy.
So Anthropic developed a system where they give the AI a written constitution, a literal set of text principles like choose the response that is most helpful and least likely to encourage violence. The AI evaluates and critiques its own outputs against those principles, generating the preference data autonomously.
So we have SFT for the format and DPO or constitutional AI for safety and tone. But if we look at the very bleeding edge, the absolute frontier of 2025 and 2026 research, we are seeing a massive shift toward RLVR and GRPO. This feels like the next leap. Let's start with RLVR reinforcement learning from verifiable rewards.
RLVR represents a paradigm shift away from subjective alignment. With RLHF or DPO, you are ultimately training the model on human vibes, what a human rater thinks sounds pleasant or helpful. But human vibes are useless if you are trying to solve complex logic.
Right, math doesn't have vibes.
RLVR is purely objective. You use this for domains where an answer is definitively mathematically right or wrong.
Domains like advanced mathematics or software engineering.
Exactly. Does the quadratic equation balance correctly? Does this Python script actually compile, execute, and pass all the unit tests without throwing an error? You don't need a human to rate that. You use an automated verifier, a compiler, or a math engine to check the final output. It gives a strict binary reward. 1 for pass, 0 for fail.
Which instantly solves the hallucination problem for coding, right? It prevents the model from reward hacking, meaning it prevents the model from outputting something that looks incredibly confident and well formatted, but is functionally broken.
Correct. The verifier only rewards functional truth, not eloquent falsehoods.
And to run this verifiable reward system, the leading labs are using GRPO group relative policy optimization. DeepSeek R1 popularized this heavily in the literature.
Yes. GRPO is fascinating because it solves the other half of the memory problem that standard PPO had.
Right.
Earlier, I mentioned PPO uses a reward model. Well, it also uses a critic model,
A critic model.
a massive neural network whose only job is to estimate a baseline score for the state of the model. So the RL math knows if an update is relatively good or bad.
That sounds like a massive waste of VRAM.
It is. So GRPO eliminates the critic model entirely.
How do you grade an update if you don't have a baseline critic?
You grade on a curve. Instead of using a neural network to guess a baseline, GRPO samples a group of responses to a single prompt. Say it asks the model to solve a math problem, and it lets the model attempt it 10 different times, generating 10 distinct reasoning paths.
Okay, 10 attempts.
It runs the automated verifier on all 10. Then, it computes the advantage of each response relative to the average score of that specific group.
Oh, I see. If the group's average score is a 5 out of 10 and one specific reasoning path manages to score an 8, it receives a positive mathematical update. If another path scores a 3, it receives a negative update. You don't need a massive critic model. You just use the group's empirical average to establish the baseline.
Exactly. And by eliminating that massive critic model, you save roughly 50% of your total GPU memory.
Wow. What do they do with all that freed up memory?
They pour it into the context window. It allows the model to generate massive, sprawling, long-chain reasoning paths. The model is given the space to explore different solutions, hit a dead end, write out a self-reflection, correcting its own mistake, and try a new path, all before outputting the final answer.
But this brings us to what I consider the most compelling part of the entire deep dive, the great debate. And I want to make sure we represent this perfectly objectively, because the scientific community, the people actually building these systems, are actively fighting over this in the 2025 and 2026 literature.
It's a huge point of contention.
Does this reinforcement learning, this RLVR, actually create new reasoning capabilities in a model, or does it merely amplify what was already there?
It is a profound, entirely unresolved scientific controversy. On one side, you have highly influential papers like Yu et al., a widely cited NeurIPS oral presentation. They conducted rigorous empirical tests. They found that if you test an RLVR-trained model on a metric called PASS at 1, meaning you give the model exactly one, try to answer a complex logic question, it utterly destroys the base model. It looks vastly smarter.
Because it learned how to think.
But wait,
Yes.
Yu et al. Then changed the metric. They tested the models on high pass at K. This means they let the raw,